organisers for putting on this great meeting in an incredible city. So my name is Benjamin Giblin. I'm a research fellow at the University of Edinburgh, formerly actually at Barcelona. And this talk, as you can see, is about slicing through the tension, how we can get improved cosmological parameter constraints from weak gravitational lensing, also known as cosmic shear. So this work was published on the archive. You can find it here. It was done in collaboration with Yan-Chuan Chai at the University of Edinburgh and Joshua Anwar at Newcastle University. So without further ado, this is what's coming up in the talk. How does cosmological weak lensing or cosmic shear work? We had a great talk on this morning from Marika, so I know you're all experts, but it's always good to refresh our memory. I'll then talk about how we might do better in this analysis using a new statistic which is called the lensing PDF. I'm going to show some cosmological constraints from this new approach and then have a little look to the future. Okay, so cosmological weak lensing, also known as cosmic shear. As we all know, this is a probe of cosmological parameters, and it relies on observations of tens of millions of galaxies out to redshifts of typically around 1.2. And so these are your galaxies, the light from which travels through the universe, and that light is deflected by the space-time curvature caused by stuff along the line of sight, typically your large-scale structure. And this bending of light causes weak distortions, also called shear, to manifest in the observed images of these galaxies, which are these things down here. They're supposed to be distorted versions of these background galaxies. And the way we typically probe cosmological parameters is we measure the shapes of these tens of millions of galaxies, and then we measure the correlations in those shapes as a function of their angular separation on the sky, and also as a function of their redshift. So this produces a statistic which is called the shear correlation function. And that produces cosmological parameter constraints that look like this. I think Marika might have shown this earlier today because this is from her paper. These are the results from the most recent cosmic shear analysis from the Kilo Degree Survey, or KIDS. So you've got the constraints on the matter energy density in the universe and the amplitude of the matter power spectrum. And these three banana-shaped contours all come from weak lensing. They are the shear correlation function and then two different transformations of that statistic. So they're all quite similar approaches. And we get this degeneracy because in lensing we can't tell the difference between a universe that has a lot of matter that is not very clumpy, or a universe that has less matter but clusters very strongly. So that's why you get the banana. Of course, here you can see the Planck contour, and the lack of overlap is this S8 tension, which we're all interested in. So these statistics that produce this banana-shaped contour, they're what we call two-point statistics, which means they extract information from the field up to second order. So what that means is if your field was completely summarized up to second order, i.e. a Gaussian, then these statistics would be optimal. But of course, the universe isn't so kind to give us a Gaussian density distribution. The large-scale structure of the universe is non-Gaussian on account of non-linear growth of structure at late times. So, in other words, these statistics are not optimal. There is information that they don't extract, and if we could extract that information, these contours would shrink, and we'd have a deeper insight into this tension. Maybe it would get smaller, maybe it would grow larger, maybe it would stay the same. We only know if we pursue a new way of analyzing this data that can extract this extra information. So that's what I'm going to be talking about. So this new method that I'm going to advocate, it relies on reconstructing the projected density along the line of sight, which you can infer from weak lensing. Because you've got observations of tens of millions of galaxy shapes, and where the lensing is stronger, you can infer that there is greater projected density along that line of sight, and where the lensing's weaker, vice versa. So you can map out these density hotspots and cold spots effectively. So these are 3 maps of projected matter density from simulated universes, and they're actually the exact same simulation and the same simulated patch of sky. The only difference here is the amount of smoothing that we apply when we reconstruct this matter density. And essentially, we have to apply a bit of smoothing when we perform this kind of analysis with the data, because the data has all these sort of imperfections, it's got holes in it, it has noise, and they manifest in systematics in these maps if you don't apply smoothing. So you have to apply some, but you have a choice about how much you apply. And what I'm saying here is that depending on the amount of smoothing you apply, you extract different features from the maps. If you apply a low amount of smoothing, you get a lot of small-scale information in the map, but you also get a lot more noise features. And if you apply more smoothing, then you lose all that small-scale information, but you might get something that has less noise in it. So now I'll talk about the statistic that I'm advocating we can use that is based on these maps. And the statistic is called the lensing PDF. It's very simply defined. It's basically just taking a histogram of your density maps. You count how many pixels there are in different density bins. So this is what this plot is showing. You've got density on the x-axis and the lensing PDF on the y-axis. And you can see as you increase the smoothing on the maps, the PDF gets gradually narrower, and that's because you reduce the abundance of very high density and very low density regions in the map. Okay, so we can measure the PDFs from these different maps and get information from different scales and potentially more cosmological information is the idea. So why should we measure this statistic? Well, it is sensitive to cosmology. Here it is as a function of changing omega n and of sigma 8. And as you increase these parameters, you get broader PDFs because you get more regions in the map that are either extremely high density or extremely low density. Okay, and essentially these PDFs don't look non-Gaussian. That's because they're actually measured from very simple Gaussian fields, but if you measure this in the real universe, you do get non-Gaussian tails, and that's where that extra cosmological information is to be had. Okay, so let's check, does this new statistic actually produce good cosmological parameter constraints? The first thing we wanted to do was a simple sanity test with simulated Gaussian fields. So in this case, your 2-point statistic that we normally use in weak lensing is going to be optimal. Here you've got the constraints on omega n and sigma 8 again, and the blue, grey, and red contours are all from the lensing PDF as you increase the smoothing. And what you see is you get this rotation, so you get a breaking in the degeneracy on these parameters, such that when you combine those 3 things, you get an orange contour which lies just here. So it's much tighter, and that is telling you that there is information on these different scales that these maps smoothed with different kernels can extract. You can compare that orange contour to the black contour, which is the lensing power spectrum. That's just the Fourier transform of the shear correlation function. So it's a statistic that's typically used in these types of analyses. And because this is a Gaussian field and this is a 2-point statistic, this black contour is the optimal result. So we shouldn't outperform that contour. And indeed, you do see that the black contour is a little bit smaller than the PDFs. And when you do the combination of all these statistics together, which gives you this dashed pink contour, it's exactly the same as the power spectrum. So that's telling you the power spectrum extracts all information from the field, the lensing PDF doesn't have any information that it doesn't already have. And that's because it's a Gaussian field. So So it's exactly what we would expect. We pass the sanity check. But let's look at what this looks like for a non-Gaussian field. Now it's log normal. These contours all have the same meaning as before. And now the combination of all these PDFs produces this very, very tight orange contour, which significantly outperforms your 2-point power spectrum. And now when you combine all these statistics together, giving you the dashed pink, that produces the exact same result as the lensing PDF. So the shoe is on the other foot now. Instead of the power spectrum being the optimal statistic, because this is a non-Gaussian field, it's actually the lensing PDF becomes the optimal statistic. So this is what we hope to see when we take this towards realistic data. So let's move now towards more realistic cosmological fields. Here I'm showing you the likelihood that you have to evaluate to get cosmological parameter constraints. It's the probability of your data D given cosmological parameters pi. It depends on a covariance matrix, sigma, that you can estimate from simulations. But it also crucially depends on your model for your parameter as a function of cosmological parameters. So this is kind of the first obstacle, is how to model the cosmological dependence of the lensing PDF. Because previously to this work, we didn't have an analytical prescription for this as a function of cosmological parameters that was valid on the small scales that your shear correlation function is. So we had to build a model for the lensing PDF as a function of parameters. And here we have n-body simulations that come to our rescue. So here are the input cosmological parameters for a suite of simulations called CosmoVerse that I co-developed with Joachim Anwar Barat and Benjamin Joachimi a few years ago. So these simulations vary in omega m, S8. S8 is the combination of omega m and sigma 8. The Hubble parameter and the dark energy equation of state parameter. So what we do in this analysis is we measure lensing PDFs from all of these simulations, and then we train a Gaussian process emulator to learn the dependence of those statistics on these input parameters. So essentially it's a machine learning algorithm. What it learns to do is interpolate between these points in this four-dimensional space in order to be able to make a prediction for your lensing PDF statistic at arbitrary points in this parameter space. So that satisfies this thing. We now have a model for this statistic as a function of these parameters, and we can we can constrain cosmology. Okay, so I'm now going to show you some cosmological parameter constraints that are all from simulated data. Oh wait, no, first of all I'll show you the lensing PDFs. Okay, these are measured from the simulations. Again, you've got density on the x-axis, and you've got the lensing PDF on the y-axis. So here we've got different panels, and that's because we measure these statistics in different redshift bins, in the same way we do with the shear correlation function. So these are the measurements from the lowest redshift bin, which is 0.1 to 0.3, and out here is the highest redshift bin, 0.9 to 1.2. These off-diagonals, this is where you take the information from different redshift bins. You take the galaxy shape measurements, and you construct a map that uses the information from different redshifts. And then you can measure the PDF from that map, which contains information from different epochs in time. And that produces all these measurements. So these are kind of the equivalent of the cross correlations, but the lensing PDF equivalent of that. So this is basically the measurements that we train our emulator on, and they're color-coded as a function of S8 there, so you get an idea for the cosmological dependence again. So that 5? Great. So let's show some cosmological parameter constraints. Here we ran an MCMC for simulated data that's tailored to match the most recent data from KIDS. So it matches in terms of the galaxy shape noise, in terms of the redshift distributions of these galaxies, and in terms of the number density. And you can see the constraints on omega n, SA, Hubble, and W0. So here, again, we've got red, grey, and blue constraints that correspond to your lensing PDFs measured on different scales, extracted with different levels of smoothing. That's what those numbers represent. And the combination, again, gives you an improvement in the constraining power, which is telling you there's information in these statistics on different scales. But how does it compare to the shear correlation function? This orange contour is the same one that we just saw. It's the combined PDF. And in black, we've got the constraint from the shear correlation function. So the PDF is already slightly outperforming the correlation function, but when you combine the PDF and the correlation function, you get a massive improvement in constraining power of about 50% for S8, 45% for W0, for example. So this situation here, it looks a little bit different to before with a simple log normal field, where the PDF alone outperformed the 2-point statistic. It appeared to be the optimal statistic for that field. And the reason we're not seeing that here, you only get these big improvements through the combination of the two statistics. That's because of the noise that's present in these simulations that we put in on purpose to make it look like a stage 3 survey, i.e. a current weak lensing survey. If instead we simulated a future survey, like the one that is going to be conducted by LSST, it's a different story. So here we've got the correlation function constraints again in black, the PDF in orange, and the combination in dashed pink. What we're seeing is the PDF constrains these parameters much more tightly than the correlation function by around 85 to 98%. And that the combination of the correlation function and the PDF yields no extra information that the PDF doesn't already have. So again, the PDF has moved back to being the optimal statistic, and that's because this is a much higher signal to noise survey. What this is telling you is that the PDF is negatively impacted by noise. It makes its cosmological dependence less sensitive, but if you increase the noise, as we are going to do with these future surveys, the gains on cosmological parameters are very significant. So, to summarize, there's information in our data that's beyond second order that we are not extracting with our conventional cosmic shear statistics. The lensing PDF is one way to get at it because it measures the non-Gaussianity of the field directly. We can measure the lensing PDF on different scales, and that's a great way to get more information out of the data. For a current stage 3 weak lensing survey, we get these kind of improvements on parameters, not bad, but it's the future with surveys like LSST and Euclid where this approach is really going to shine. So you can see more in the paper at this archive link, and I'll take questions. Thank you.
Yeah. I was wondering, thanks for a really nice talk. I was wondering if your method can both shrink error bars but also limit biases. Is it so that the current two-point statistics are somewhat biasing themselves?
That's a really good question. So, in case everyone didn't hear, the question was, this approach seems to shrink error bars. Can it also reduce biases in the parameter constraints? And that is something that really represents, I think, the next stage for this analysis because what we haven't looked at in this paper is the way in which the lensing PDF is impacted by all of the systematics that weak lensing is prone to. So one is the intrinsic alignment of galaxies. We have actually looked at that a little bit. This was one plot that shows the bias in the lensing PDF as that is caused by intrinsic alignments, and that's shown by this pink thing. And you can see the size of it relative to changes in S8. So how you get a flavor for how big the bias is going to be compared to like the bias it would cause on S8. But yeah, what we need to do is progress this through in an MCMC to see, is it a bigger bias than it causes for the shear correlation function, or is it smaller? I guess the short answer is we don't know yet, and there's a bit of work to do with systematics for this statistic before it can be competitive with your conventional shear correlation function.
Okay, someone else? Yes?
I was a little confused about why your training PDF curves looked really Gaussian.
Yeah, that is because of the noise present in the simulation. So we're adding intrinsic ellipticities to all of the galaxies in our simulation, and they're sampled from a Gaussian because that's essentially how the noise manifests in the data, and we're trying to mimic that. So by adding all these Gaussian random numbers to our simulated galaxies, it really makes these things end up looking very Gaussian.
Aren't they supposed to, isn't the power of the method them being non-Gaussian?
Yes, and so I would say that you can't see it by eye, but yeah, there is non-Gaussianity in our data as well as in the simulations that, yeah, you have to take my word for it, but you can't see it by eye, yeah.
Okay, someone else? No? Okay, so let's